So, just like there are two methods of doing this with continuous, there are two methods of doing this with discrete as well. And you might already have asked yourself from that last question, well, how many out of 20, they cured 11 out of 20 last time, how many out of 20 would it have to have been that we did accept that the new drug is better? And that comes really from looking at it from the critical value approach. So what we're going to have now, well, let C be the critical value. So in this example that we've just seen, that would have been, well, how many patients would they have had to have cured out of the 20? That's what that C would be. To assume that, or to accept that the new drug actually was better. Well, we want then the probability that we would have observed this critical value, or even more people cured than that, going back to what Tom asked a minute ago off camera. We want the probability of getting that to be less than, I'll put in or equals to, it doesn't really matter, I suppose, our significance level. So we're trying to find now a critical value such that seeing that many people cured, or more than that, would have had a less than 5% chance under the conditions of H0, null hypothesis. This is a greater than, though. We don't like greater than. We need to change it round into a less than or equal to. What is the opposite of greater than or equal to C if I'm going to write down a less than or equal to inequality here?
Do you have to put 1 minus P and then C minus 1?
Say that last bit again?
C minus 1?
Yes. Okay. The opposite of greater than or equal to 95 is less than or equal to 94. So this C minus 1 here is really important. And I'm turning that around. What will this number over here be then? So I'm turning all of this around the other way around. Yes, 0.95. Okay. And I'm turning it round because our tables are less than or equal to tables. And this fact here, that this now is C minus 1, that is quite important, that you actually remember to do that. So what we want to do now is we want to go to our tables, and we are going to use the n is 20, the p is 2/5, which is 0.4 as a decimal. And what we are trying to find is the first probability in our column which is bigger than 0.95, greater than, well, probability greater than 0.95. So look at your n is 20, p is 0.4, go down that column, find the first number that is bigger than 0.95. What is that probability, and what is the x value that goes with it? 0.9790, yes, and the x value that went with it is 12. Right. So that 12 pairs up with that C minus 1. So our C minus 1 is 12, which means that C is 13 or better. So that means in the trial, if they were going to trial it with 20 patients, to conclude that the new drug was better, we would have wanted to see 13 or more people cured. So that 13 there is our critical value. And we would make our decisions that if 13 or more out of the 20 people had been cured, we would have rejected H0, which means we would therefore have accepted H1. And to be honest, whilst the first method is easier, I think if somebody was asking you if the drug manufacturer was asking you to do this, they would be more interested in this. So they'd want to know, oh, we were 2 people off, were we? You know, how close were we? We were 2 people off.
How can we change the results to make sure?
How can we fiddle the figures? No, not how we can fiddle the figures. No, we need to make our pill better. Okay, so that's the alternative approach of finding the critical value, which gives you more useful information than just replying back to the chemists. No evidence. It actually gives them and how far off were you?
Wouldn't it be better to have a smaller sample? There would be less people on.
Well, as we said earlier, the bigger the sample, the more reliable your results.
But they want to be closer.
Yes, but you still want a bigger sample. The bigger the sample, the more reliable your results anyway. So I'm going to pause the video there and we're going to move on to a different example.